Okay, let's talk a little bit about what can affect the rate of diffusion of gases. So one of the key points is to remember that both oxygen and carbon dioxide will diffuse from areas of high partial pressure to areas of low partial pressure. That means that the alveolar partial pressure of oxygen has to be higher than that in the blood. And the greater the difference, the faster the rate of diffusion. One of the other things that's going to help with this is going to be the large surface area of the alveoli that will allow blood to come into lots of contact with oxygen. The fact that this is simple squamous epithelium that is making up the alveoli means that the diffusion distance is very small. And again, that solubility coefficient and molecular weight of gases will also influence this. So for example, oxygen is smaller than carbon dioxide. I mean, it's one carbon smaller, right? It diffuses somewhat faster. However, the small solubility coefficient means it needs to be transported by red blood cells. Conversely, even though carbon dioxide may diffuse slower than oxygen does, it does dissolve more easily in water. So if we take a look at this, what you're seeing here in this image is here's an alveoli, here are capillaries in our bloodstream, and here are cells giving off carbon dioxide. So what you're seeing is that most of the oxygen is going to be carried by red blood cells. Very little of it, like 1.5%, actually dissolves in the bloodstream. However, carbon dioxide, a larger amount, so about 7%, will be dissolved in the bloodstream. The vast majority of carbon dioxide will be transported as bicarbonate ions, and then some of it will bind to red blood cells as well. However, the carbon dioxide that binds to red blood cells does not bind in the same location as the oxygen does, so they don't necessarily compete for the same binding sites. Okay. Again, the most important factor that determines how much oxygen will combine with hemoglobin will be the partial pressure of oxygen. One of the key things is that remember there's 4 heme molecules, right? When that first heme binds, it'll actually change its shape slightly, which makes the second oxygen bind even easier, so that next heme molecule, and then the third one binds even easier, and then the fourth one binds even easier than that. Okay. And you don't have to memorize these numbers, but basically in areas like where they're working muscles, contracting muscles, the difference in the partial pressure will be one of the triggers that causes oxygen to unload from or be released by the red blood cells and travel to those working muscles. Other things that are going to affect the affinity of hemoglobin for oxygen, these will all be related, again, to things that we would see in working muscles. So acidity, partial pressure of carbon dioxide, temperature, as well as something called BPG. So as acidity increases, the oxygen affinity for hemoglobin decreases, and oxygen will dissociate more readily from hemoglobin. So meaning, again, as acidity increases, the hemoglobin will release those oxygen molecules. Now think about it, working muscles often have a buildup of lactic acid, meaning that acidity is increasing in those areas, as well as the buildup of carbon dioxide will also cause regional acidity, again facilitating that oxygen release. And what you're seeing here, this is going to be a very important equation, and it is a reversible reaction, meaning that this arrow actually goes in both directions. It doesn't just go to the right, it will also go back to the left. But what this is saying is carbon dioxide in the presence of water will form something called a carbonic acid. That carbonic acid will then turn into bicarbonate and hydrogen ions. So I color-coded that for you here. These hydrogen ions are what produces the acidity. So again, where there's big carbon dioxide buildup, you often get acidity. Just as an FYI to you, we're going to see this again in the digestive system. This is how we make the hydrogen and hydrochloric acid for our stomachs. We will see this being used in the kidneys. So this equation comes up quite a bit in anatomy in the body. It is a very common formula, or I guess very common reaction to occur. This is also how, just as an FYI, this is how we get ocean acidification to happen. The water in the oceans picks up the carbon dioxide in the atmosphere, producing hydrogen ions. And this is also how we get acid rain. So anyway, it's a very common, I guess, metabolic reaction that occurs both in our bodies and in nature. Okay, basically this slide is simply saying what I mentioned to you in this top bullet point. So hemoglobin acts as a little bit of a buffer for hydrogen. So again, as pH decreases in areas, the hemoglobin molecules will pick up hydrogen, unload oxygen. But in areas where there's high pH, basically it picks up oxygen and releases hydrogen. So it can, hemoglobin can act as a buffer. So again, picking up hydrogen where there's lots of it, and then releasing it where there's very little of it to maintain the proper pH in the body. Carbon dioxide, as I mentioned, also binds to hemoglobin. And as the partial pressure carbon dioxide increases, again, oxygen is released more easily from those hemoglobin molecules. I mentioned this to you in the earlier slide. About 7% or 5 to 10%, depending on, like 7% average, 5 to 10% is your range of carbon dioxide that is carried by the blood as a dissolved gas, just like we would see in soda. About 5 to 20% binds to amino group of globin. So it doesn't bind to the heme part like oxygen does. It binds to the globin part to form something called carb-amino-hemoglobin. Again, it doesn't compete with the oxygen. But however, the hemoglobin molecule can also transport carbon dioxide. But the vast majority of the carbon dioxide will react with water, as we saw a moment ago in this reaction, and is transported as bicarbonate. Similarly, temperature will also impact the strength with which hemoglobin holds on to oxygen. So the higher the temperature, the more readily the hemoglobin releases oxygen molecules. So again, this is where we would see elevated temperatures in things like working muscles. Now, BPG is a metabolic intermediate of red blood cells. It binds to the deoxygenated hemoglobin, and it causes them to change shape, and it also promotes the oxygen unloading near tissue. So it's just yet another mechanism for the unloading of oxygen molecules. So hemoglobin does not just, I guess, carry them around and around and around the body without letting them go. Okay, so just kind of going back, some of the big ones again are acidity. So again, think of what working muscles are going to show. So they'll have a higher acidity level, more carbon dioxide, they will be hot. So all of those things will cause the unloading of oxygen molecules near working tissue. This BPG also will result in the unloading of oxygen molecules. So again, a hemoglobin does not just hold on to an oxygen molecule without ever letting go. So these are all your factors that basically will determine where oxygen is delivered. So its unloading is not random, but rather it is preferentially unloaded in tissues, muscles, or organs where there's high metabolic activity. Okay, hopefully that makes sense. As always, if you have any questions, please let me know.